Hi, I'm Jonathan Lowe, a senior systems engineer with AGI, and today I'm going to talk to you about multi-int mission planning. So recent years have seen a dramatic increase in the number and type of sensors available across a wide range of platforms. Visible and IR imagery, synthetic aperture radar, signal detection, direction finding, and even geolocation capabilities are now commercially available on land, at sea, in the air, and on orbit. So one such example is HawkEye 360, a company using a constellation of satellites to build a global geospatial RF spectrum map. They advertise the capability, among other things, to track maritime traffic by detecting, decoding, and geolocating the Autonomous Identification System AIS signals from ships at sea. So for organizations that care about detecting and tracking moving objects, mission success depends now more than ever on the ability to model and plan how to use all these different types of platforms and assets and these intelligence gathering systems together rather than in separate stovepiped systems. So in other words, the ability to handle any platform, any payload, anywhere, any wavelength, all in a single mission planning environment is critical. So let's take a look at what this type of analysis can look like for a notional mission against suspicious maritime traffic off the coast of South America in the Pacific Ocean, incorporating these and other commercially available platforms. Okay, so in my STK scenario here, we have, again, our notional constellation of 3 HawkEye satellites, and they're going to be passing over this part of the Pacific Ocean. So we have a cargo ship in the area that's going to be transmitting AIS data as it's navigating north. And so we kind of watch here. So around 11:15, the satellites start detecting the signal and pass overhead. So what we actually have going on here is a dynamic communications link budget analysis. Anytime you're doing this type of dynamic comm link, there's a few things that you're going to want to be able to model. The first is flexible and accurate modeling of the transmitters and receivers, so you can easily swap in and out those different payloads and their specs. The second is a user-definable environmental model for the RF effects, especially for edge cases. Next is going to be signal quality metrics. So for things like signal detection as well as acceptable data transfer, and also realistic dynamics, both for the platforms themselves as well as antennas and even antenna gains if it's something dynamic like a phased array antenna. Okay, let's see here. All right, so the cargo ships are required to transmit an AIS signal, which is pretty well defined, the transmitters and all the specs for that. So we're actually able to model that signal pretty well in STK. So if I look under my cargo ship, you can see I've modeled both of the different channels. We'll just take a quick look at the settings here. You see we've defined the frequency, power, data rate, even an antenna model, the modulation, etc. So all of this is modeled here as well. So let's take a quick look at what the signal is going to look like from the perspective of the ship. So using STK's spectrum analyzer, which is basically a digital model of this here. So we will change our settings. Take a look at it there. All right. So now as I look at my scenario here, I get my spectrum analyzer on one side. I'll get the HawkEye guys coming overhead right there. So as we animate through, you'll notice that I've got here's my signal, and oh, hang on a second. There it goes. That's the scale I wanted. All right, so now we see the signal is increasing and decreasing. We see some Doppler shift happening in the frequency domain, but we see there's some pretty dramatic rises and falls happening in this signal. So the first question is, what's going on there, and is that realistic? So what we may want to do is take a little closer look at the signal behavior. So I'm going to run one of our pre-generated report styles, which is going to be received isotropic power. So now we'll kind of look at the same signal characteristics, but in the time domain. And you can see that we have pretty wide variations, almost 50 dB over the course of this pass. And there's gradual rises and steep falls and just kind of chaotic looking behavior. So what's going on here? We'll take a little bit of a deeper dive and look at the link budget parameters in some detail. So as we zoom in here, we can look at all the different loss effects that are happening. So you can see at the start and end of the pass, there's some tropospheric scintillation that's being taken into account. But the main culprit is actually the ionospheric fading. You can see it varies widely in here. So what's actually happening is that we've turned on the ITU provided model for ionospheric fading. And what it's telling us essentially is that at this frequency, we can expect to see some very large, rapid, and chaotic changes and unpredictable fluctuations really in our signal strength. So that's what these steep drop-offs are actually representing for us. So the question now is, the people that designed the specs for the AIS system, did they take into account this potential ionospheric effect such that the power and everything still results in a good enough signal? So we can actually continue scrolling over in our link budget, and we'll look at C over N naught and then a bit error rate, and you can see that we actually have a pretty strong signal as well. One thing that we've also done here in this model is we've set a cutoff threshold of a bit error rate of 10 to the minus 4, and we've applied that to the receivers actually on our satellite. So if I take a look here at my AIS receiver and go into the communications link constraints, you can see here bit error rate 10 to the minus 4. So, yep, it looks like we actually are going to still get a good signal for this. Okay, so the next thing we want to take a look at is what are the actual times that we can get this signal link here. So we've got some other quick things we looked at. So where is my report? Oh, here we go, AIS uplink times. So we've actually generated a time dynamic graph, just give me start and stop times when I meet that bit error rate threshold for each of the channels across each of the satellites. And you can see them color-coded and overlapping here. So what we can look at next is one of the location mechanisms, which is looking at Doppler shift crossing. So essentially, as the signal Doppler shift varies as it crosses 0, that's going to be the time of closest approach to the emitter of that signal. So again, we'll take a look at some other elements here. I've got on my complete list of reports here, I've got my Doppler. So now I've generated my Doppler shift report and graph actually. So we can take a look at whenever it crosses 0, that's going to be the time of closest approach, which will happen right about there. Yep. So I can both eyeball it, and I can also, of course, generate the actual numbers. So what is the times of my Doppler crossing when I actually go across 0? And then I can also look at what's the lat-long altitude of my sub-satellite point at those times. So this gives me sort of the lat-long box of where I think this closest approach would be. And so that's what we've actually turned on in this red area here, adding a little bit of margin. So that's one approach to finding and locating a signal based simply on the signal detection parameters. The other approach, of course, is geolocation. So in order for that to work, you essentially have multiple receivers that receive the same signal at the same time, and they'll do time difference of arrival and frequency difference of arrival measurements between those detectors. And then they can use some algorithms to find exactly what spot in space produce that signal at that time. So the first requirement there is we need 3 detectors detecting the same signal at the same time. So the question then is what's the first time at which all 3 of my satellites can detect that one signal to the right signal quality? And so that's my geolocation intervals report. So I can run that real quick, and we're basically combining those access visibility times and rolling them all up into one set of times here. So we're looking at October 12th at about 11:16. There we are. Okay, so the next step then is we can actually use AGI's orbit determination toolkit called ODTK, and we can ingest those signal detection times and the rest of the dynamics model from STK. We can then simulate realistic TDOA and FDOA measurements on those satellites, or if we had real measurements, we could use those too and do real data processing. And then run through ODTK's algorithms and produce that geolocation as a function of time with the error ellipse on the ground, and then push those results back into STK. So let's take a look at that kind of results here. So I'll jump to my stored time. So here we see a view of my cargo ship. There's 3 satellites coming overhead, and as I animate through, you'll notice we've got these error ellipses coming in. So what this is showing you is, over a short period of time, ODTK is simulating these measurements, it's processing them, it's generating the error ellipses, and you can see that they're growing and shrinking over time, and we're comparing that the estimated position in yellow to the truth position in green. And you'll notice that as you get more favorable geometry, in other words, when the satellites are more directly overhead, your errors shrink down quite a bit. So you can actually get some, very tight, very realistic results here. So as a quick question is like, how close did we get? So we've got a graph here, which is our range to the ship. So this is our estimated position to the truth, and we're, down in some cases, well under 100 meters, under 50 meters even, as we're moving along. So of course, as the satellites get much further down on the horizon, the errors and uncertainties grow quite a bit. They're changing around. Okay, so the next step is, let's suppose that the reported position in the AIS signal does not line up very well with the geolocated signal. So that might be an indication of suspicious activity. Maybe you want to check something out. Maybe it's a problem, or maybe it's actually malicious. They're spoofing something. So the next question is, how do I bring other assets to bear to figure out, kind of what's ground truth in this situation? So the next question is, how quickly can I get some satellite imagery in this area of interest to better assess the situation? All right, so what we're going to do next is we're actually going to use STK's coverage module, there we are, to look at when some various imagery satellite constellations come overhead. So essentially the question is, who is going to be able to search this area the soonest? So we're not interested in just a single point, we're interested in kind of area coverage. So we've got a couple of different coverage definition objects turned on, and what we're actually seeing here, the metric is the time in hours until the constellation passes overhead. So if I turn my legend on, it's here, you can see response time in terms of hours. So for instance, Cosmos SkyMed, he's almost immediately overhead, but he's only going to get one portion of my search region, so that's maybe not optimal. And we can just sort of cycle through and see the other results. So there's Pleiades, he gets the whole area in about 4 hours, and RapidEye, it's part of the area 4, part of it 5. Let's see, Worldview, I'm also considering, he's like 5. So in this case, it looks like Pleiades is probably my quickest option. So, assuming I can work with them and task the right stuff, get the right imagery orders, we'll just assume that maybe I'm going to go for Pleiades. Okay, so of course, simply being overhead doesn't tell you a whole lot about the quality of the image this satellite might be able to take. So the next step is to refine the prediction a little bit more with some performance metrics. In this case, we're basing it on open source specs. Of course, if you're talking with the manufacturer or you are the manufacturer, you can put in much more detailed models. But some of the things we care about are going to be, say, elevation angle. In other words, how high, what's your perspective, sun elevation angle, so what's the shadowing going to look like, and also image resolution. So these are just kind of relatively quick and easy metrics that you can calculate. And we've got here a report for the times of interest. So we're looking at the passes that are at about 12 October 1600. So you can see my elevation angle. So it gets pretty high, almost 80 degrees. The ground sample distance potentially could be under 10 meters. Sun elevation angles are pretty decent, right? So all this says, yeah, this might be an image I actually would want to take. So we could potentially go off and task that. So let's again, this is a notional example. Let's assume that we got this imagery, which was enough resolution to be able to kind of pick out a large cargo ship in the open ocean. And we say, okay, yep, I found the ship, and it does not match what the AIS signal said it was. So there's something fishy maybe going on here. Let's see if we can get an even closer look. So what we do next is we say, hey, digital globe satellites, the Worldview satellites, now Maxar Technologies, those guys are going to be overhead very soon after. So maybe we can get them to take a really high resolution image shot and just see what we can see. So the next thing we might want to do is going from these kind of general, imagery satellite metrics to a very high resolution simulation. So to do that, we're going to use the EOIR module inside of STK, which allows you to really go to a lot higher fidelity here. So if I bring up my satellite, it's Worldview 2. So let me take a look at his properties and just show you how we model this. So in EOIR, we have the ability to model the spatial, the spectral, the optical and the radiometric properties and sensitivities of a given sensor. You can start off kind of, with ballpark specs, things typical that you see out there, or you can actually get really, really down into the weeds depending on what you're trying to accomplish. All right, so we're going to pick this image. We're going to find the right time when the Worldview satellite might actually be overhead. And there we are. Let me pull him on. Get back to my right time. Okay, so here's the perspective of it. And now we're actually going to go off and simulate that image using EOIR. Okay, so now that EOIR has finished rendering the module, we can see that we have applied a custom 3D model to represent the size, shape, and materials of the ship. So we're actually getting, individual pixel representations here with shadowing and lighting, etc., and we can actually get much more detailed spectral properties for this. But even just a quick glance shows that, hey, here's the image of my ship, and there's some other kind of gray blip right here. So to me, maybe that throws up a red flag. If I'm an image analyst, I say, I think maybe there's another small ship nearby. So it's sometimes known that illicit cargo exchanges happen out at sea. A small boat rendezvous with a big one, and they offload stuff they are not supposed to be doing. So this might alert a situation where you say, hey, I want to send the Coast Guard to go interdict this. Maybe you suspect that it's narcotics or something headed for the U.S. All right, so let's move on to the next phase. Coast Guard ship. All right, so here we've modeled a couple of Coast Guard ships that were in the area, and we've got a path for the cargo ship and the other small boat in the region. So we're going to send these guys in to see what they can see. So there they are. They're sailing away. So as one of the Coast Guard ships is en route, it's actually going to launch a ScanEagle UAV with a synthetic aperture radar platform to go search the area up ahead. So the first thing we want to model is actually the route of this ScanEagle platform. And you can see we're actually modeling how it launches off at an angle because it's sort of catapulted up. And then using STK's aviator model, we can plan the whole route according to the performance limits of this UAV. Everything from speed, acceleration, attitude rates, fuel usage, etc. We can actually tell it, hey, here's my search area of interest. Go make a grid, fly that out for me. So that's what we've done. And then you can see the flight path in dashed yellow coming up here. We've got a few other things as well. So we're modeling in sort of a generic sense, in this case, the SAR collection footprint, which is these yellow patterns coming off the side. They'll look a little more like you'd expect once it gets up to altitude. And then also we're modeling the command and control and video SAR links back to the ship for its entire route. So we're basically saying, what's a realistic route that I could actually accomplish with this ScanEagle, and could it, go search my area and maybe find this ship, the cargo ship or the fast boat or something, well before my cargo ship, my Coast Guard ships actually get up there. So we'll take a look at that. So there he goes, launching up. You can see the comm links happening. And in a moment here, he's going to get to altitude, make a nice little banking curve. All right, so we'll zoom out and just watch that happen. And there he goes, he turned around. Okay, so this is kind of the SAR pattern you'd expect. And if I zoom out a little bit, you can actually see out here, out in the ocean. So here's the search region that I have based on my kind of last known location of where the ship and that other boat was found, and we've calculated a search grid with spacing such that we maintain coverage and link quality. Right, so he's off and away going to be doing his searching. Okay, so as the two Coast Guard ships are approaching, they also have their own navigation radars, and so the other thing we can model is the performance of these radars out at sea, and say when might they be able to detect something with a large RCS like the cargo ship and something with a very small RCS like the fast boat, and figure out when that's actually going to happen. So to do that, just like we modeled the transmitter on the comm side, we can also model the search track radars on the ships with similar performance parameters. So we've got PRF, pulse width, modulation, probability of detection, transmit frequency and power, etc. Whatever is appropriate for this ship. So we've got our two ships on their routes. And you'll notice that they're both sort of tracking these objects, and so we can look at actually the predicted radar performance for each of these guys. So I'm going to look at my search track, integrated SNR, and PDET. So in this case, it's for ship 1 to the cargo ship. And you can notice that there's a pretty big spike right around here at this time. And so that tells me this is the signal detection time when I'm actually going to start getting a ping on that cargo ship as it gets close. And we could also look at, right, so this is actually where you would change course to go interdict the cargo ship as he detects them. So then there's also a time as these two cargo ships are approaching where both of their radars can now detect the fast boat. So maybe they both get a signal, you know, hey, I've got a hit at this azimuth, possibly this range, got another hit at this azimuth, this range. And so that we could even do simple direction finding in STK to do some basic, you know, triangulation and figure out where that point would be. So we've got here we go, triangulate point. So in this case, we actually used STK's vector geometry tool, part of the analysis workbench, to do that triangulation calculation at that time and come up with a potential target point for the fast boat. So at this point, you see our scan eagle is, you know, starting its search pattern, but the Coast Guard ships say, hey, I found something more interesting. I've already got the cargo ship. I want you to actually go find this fast boat and see if we can interdict that guy. So we now tell the scan eagle to change course, which he will do momentarily. There he goes. And the scan eagle is going to fly out there and then start doing a little search pattern around that point of interest. And we'll see when he can actually detect that fast boat. All right, so there he is. Oh, he got something. He's circling back, and he's just going to, you know, hover over him until the Coast Guard ships arrive. So how do we know that he was able to detect it? So again, similarly, we are able to model a synthetic aperture radar on the scan eagle itself, model its SAR parameters, and we can look at its performance as well, which is going to be, here's my SAR SNR report. Taking a moment to generate. And there we go. So we can actually see, you know, at what point does my, you know, predicted SNR spike above 1, and it's actually going to be kind of over in this part of the graph, right? So we can take a look and see where is that. It's, you know, just barely above 1 right over here. So we can take a look, where is he? And yep, that's right, as he's starting to cross over, just kind of right inside that field of view. And so maybe that's the first ping, and then he turns around, and now as he's going to start circling around, you can see he's got a much more complete signal. So we'll just kind of watch that animate. There we go. Okay. All right, so now we've used STK as our multi-int mission planning environment. We've examined the capabilities of a lot of these commercially available platforms and sensors across a wide part of the EM spectrum. We've seen how they can work together, how you can use these capabilities to complement each other, and use them to prosecute a potential mission against suspicious activity. For more information, head to agi.com.